In the last lecture, we walked through spectral embedding, otherwise known as Laplacian eigenmaps, which is one of the older approaches to doing for doing manifold learning. And so what we're going to do now is walk through two more modern techniques that are very popular. You see them all over the place as visualizations, as data analysis tools for doing nonlinear dimensionality reduction. They're called t-SNE and UMAP. t-SNE is just the way you pronounce this acronym right here, and UMAP is just a little rolls off the tongue a little bit better. Now, t-SNE was first described in 2008, and UMAP was not published until 2018. So these are two of the more modern ways of performing this procedure. And they were both developed in a way that was really optimized for really, really gigantic data sets. So in our data matrix, where it was n measurements by n data points, these are optimized for scenarios where both n and m are gigantic, like millions of points with millions of dimensions or something like that. If you had a really, really, really high dimensional and large data set and you want to reduce it down to something that you can put into a piece of paper or a report, it's two-dimensional, what do you actually do? So these are two of the ways that people are popularly using now in order to perform this procedure. And they are related to the spectral embedding, which is why I introduced the concepts of spectral embedding first. The reason they're related is because we share in t-SNE and UMAP with spectral embedding this idea of computing a similarity matrix that is based on the neighborliness of my point to some other points. Okay, so these are my data points. So I might have some data points that are inside my epsilon neighborhood and some data points that are outside my epsilon neighborhood. And I'm similarly, just like in spectral embedding, have this notion of some kind of like a Gaussian kernel, right? Where I'm computing the distance between something and something else, and I'm actually going to put a tiny little Gaussian on top of it so that we're computing a similarity here that is something like the exponent of the negative of the Euclidean distance between these two things by some width that I can define as a parameter, right? So this is my Gaussian kernel that allows me to define the similarity between points I and j, okay? Just like in Laplacian eigenmaps. So we're going to take that concept and we are going to take it one step farther. So step one, just like in spectral embedding, is define some kind of neighborliness. There's some parameters needed to define. How many neighbors do I actually have? How close they have to be? What exactly is the shape of this Gaussian kernel? These are all decisions that we have to make just like we did in spectral embedding. So for t-SNE and UMAP, they have that in common, okay? But we're going to go one step further beyond the similarity matrix. Instead of then computing the Laplacian matrix, the graph Laplacian like we did in Laplacian eigenmaps, we're going to do something slightly different, which is to take this similarity matrix and bring it into a probabilistic interpretation. So instead of the similarity being some notion of the inverse of the distance, 1 minus the distance, we're going to say the similarity is actually like a probability. Okay, what is the probability of this being my neighbor? Something like that, okay? So once again, the goal, just like before, is to take something that is my data in high dimensional space. It could be moderately high, it could be very, very, very high, okay? I'm going to try to learn something so that we can turn it into very low dimensional space, okay? So like the most common t-SNE and UMAP visualizations that you see are 2, at most 3-dimensional. Like I've almost never seen a 4-dimensional UMAP or t-SNE that I thought was particularly useful. It just doesn't happen. Maybe the fault is my own. I'm sure the limitation is mine instead of with the algorithms. But here's the thing that I am doing, okay? So the probabilistic interpretation is the following. I'm actually going to define the probability of my data in the original space, and then the probability of whatever I have morphed it into. So this actually shouldn't be a straight line here because it's like a nonlinear embedding, right? Something happens, and I've turned my very nonlinear data into like a flat space that's lower dimensional. So whatever is happening here, I'm going to call my original data x, just like I've always done. And so there's a probability distribution of x. And then just as the notation, I'm going to call the thing that I'm projecting it into, the embedding space, I'm going to call that y, okay? And y similarly has a distribution. I'm just going to call that q. So the whole trick here is that I'm going to define p using exactly the same nonlinear tricks that we learned in the Laplacian eigenmaps. We're going to define a local neighborhood, and we're going to use a Gaussian kernel to define this P of x here. We're going to define this, okay? And then we're going to use some other tricks I'm about to tell you about to then solve for this. So we're going to define some notion of neighborliness and distance, the original data space, and we're going to use it to solve for the distribution of y. And the reason that this is a possible problem is I'm going to pose something that I'm going to be optimizing for, because this is an optimization procedure. Okay? And the thing that I'm going to be optimizing for is how similar these two distributions are. And that's the probabilistic interpretation of these algorithms. I want the probability of P and this probability Q here to be as similar to each other as possible, even though they're completely different in dimensionality. This thing could be 1,000,000 dimensional, this thing could be 2-dimensional. But I want the probabilities in a sense probability distributions to be similar. I'm going to tell you a couple of different ways that t-SNE and UMAP have formulated that problem in a rigorous way. So they're actually really similar, even though they were derived separately from kind of different backgrounds, but they have a lot in common. And so I'm going to try to highlight here what they have in common, as opposed to just going through each algorithm like they're totally different things, because they're not totally different things. And along the way, I'm going to point out the ways in which they are different. Okay, so let's get started. So let's do t-SNE on the left, and we are going to do UMAP on the right. Okay? So the first thing we're going to do is we need to define this. We need to define the probability distribution of x, my original data set. And this is where it's going to seem really familiar to you from the last lecture on Laplacian eigenmaps, because I'm going to define P of ij, the probability of my data, as essentially exactly the same thing as this Gaussian kernel that we had before, subject to the neighborliness that we had before. Okay, so it's almost exactly the same. So we're going to take the distance between I and j, okay? I'll take the negative of that, divided by some kind of width, which is another parameter that I'm going to pick. I'm going to take the exponent, okay? So far so good. This is just a Gaussian kernel. And in t-SNE, I'm actually going to normalize it. And I'm just writing the sigma down here as a shorthand for summing over all of the other stuff. So this gives you element ij. This is the sum over the entire column. So it makes it so that the entire thing adds up to 1. Okay? Now, for UMAP, it's going to look really similar to that, but slightly different. The only difference is that it's not normalized. So it's exactly the same Gaussian kernel, where you take xj minus xi, the distance, divide by some kind of width, but I'm not going to normalize it. So it's not going to add up to 1. And the interpretations of this is various, but it has some really interesting numerical computational consequences that make UMAP actually easier to compute because it's not normalized and it makes it faster. I'll get there in a second, okay? So the second thing we have to do in order to solve for Q of y is define this notion of distributions in y space, in this very low dimensional space that we're about to be able to solve for. And so Q ij is defined as 1 over 1 plus the distance between y sub j and y sub I. Okay? And this is, again, going to be normalized. Now, let's think about this for a second. So 2 points in y space. So I have, 2 points over here and 2 points over here, right? If these 2 points are close, then this number is going to be a small number. So this denominator is going to be 1 plus 0. 1 divided by 1 is 1. Okay, so this is going to be a 1. And what's going to happen if these 2 points are really far apart is that this vector is going to have a larger magnitude, 1 plus large number, and then you take the inverse of that. This is going to be a very, very small number. So this Q here is going to have the property, just like before, of similarity, where if points are close, it's going to be a bigger number because they're more similar. And if points are farther apart, they're going to be less similar. Okay, exact same thing as before. Now, maybe this will not surprise you. The definition of Q in UMAP is very similar. It's exactly the same thing, except we're not going to normalize it, just like before. Okay, we're going to take y sub j minus y sub I, take the norm of that, and that's it. That's what we're going to do. So here with UMAP, both of these things are not normalized. All right, now that we've defined how we're going to compute similarity within X and within Y, we have to be able to do some kind of optimization. In optimizations, we always have to define some kind of loss function, a target. How do we know we're getting to the right answer? How do we know we're getting close to the right answer? How do we know if we're headed in the right direction? We all have to define a loss function. And so the loss function here is based on this notion of how to compare probability distributions. And we're going to draw on this concept that's really popular in comparing distributions in statistics called the KL-Divergence. Now, KL-Divergence stands for Steinbeck-Cobbler, the Steinbeck, oh my gosh, I can't, Kullback-Leibler, the names of two individual people who were responsible for having described this. It is not to describe the difference between Brussels sprouts and bok choy. I know what it sounds like, but it doesn't. So the KL-Divergence, we can also write it as K and L. So what we're gonna do is minimize the KL-Divergence of P and Q. So we have these two distributions that we can describe and we can compute, okay? And we're going to jiggle the points around in Y, going to move them around so that this quantity, the KL-Divergence between P and Q, are as small as possible. So it's going to be an iterative algorithm we're updating. And because of the properties that are known about the KL-Divergence, we can compute it, we can compute its derivative, and so we can kind of iterate and walk ourselves to the right location, or at least to the location where nothing else is really changing, and that's the answer we are looking for. Now, the one quick sentence intuition between the KL-Divergence is that it's a description of if I had P, if I expected the world to be like P, how surprised am I if I actually saw Q? All right, so let's say that P is some nice normalish distribution over here. Like I think I'm expecting P. You know, I walk into a store, I'm expecting P. And what I actually got was Q. All right, so Q looks like this orange curve here. And it doesn't have to be well behaved. It could be lumpy. It could be like that, okay? So given that P is what I was expecting and Q is what I actually got, how surprised am I, right? And this is not a 1 or a 0. This is like a number. If I'm really surprised, then KL-Divergence will be large. If I'm pretty much not surprised, then the KL-Divergence can be small. Now, this is a general nice notion of how similar distributions are because, as you've learned in the statistics module and probability modules, you can have distributions that have the identical mean and standard deviation, but are super different if you look at it, right? You can have like a lumpy thing where it's bimodal, but it has the same mean and standard deviation as a normal distribution. They're totally different, but they have the same numbers. And so you might be fooled into thinking they're the same where they're really not. So the KL-Divergence is one way, a concrete way of computing how surprised am I if I saw this orange thing when I was expecting this pink distribution here. So if I'm going to minimize the KL-Divergence of P and Q in both of these algorithms, I end up with a loss function. So in this case, I'm going to minimize my loss function, okay? And in this case, it's going to look like the sum of every data point that's not me of Pij times logarithm of Pij divided by Qij. That comes directly from the definition of the KL-Divergence. This is the KL-Divergence right here, this P times log of P over Q thing, okay? So in the case of UMAP, technically we're minimizing something that's not actually the KL-Divergence. It's something called the cross entropy, okay? But I'm gonna write it and you'll see that it actually conceptually is very similar and related to the KL-Divergence. So here what we're minimizing is a loss function. The first term is exactly the same as the KL-Divergence. I not every other point that's not me, okay? Pij log of Pij divided by Qij plus 1 minus Pij log of 1 minus Pij divided by 1 minus Qij, okay? So this thing, so in the case of t-SNE, we're minimizing the KL-Divergence. Okay. In the case of UMAP, we're actually minimizing something called the cross entropy. But as you can see from the formulas, they are related. The first term of the cross entropy is the same as the KL-Divergence, and it has this correction term here for reasons that I will not go into right now. Now, in both cases, we now have a definition of what it means to be a distribution in the original space, what it means to be a distribution in the projected space, the embedding space that we're eventually going to get into. We have a notion of how we know we're getting close. All that's left over is optimize. And in both cases, we're going to be optimizing by gradient descent. Okay? We have a loss function, so we have the data. We initialize by a educated guess of some kind. So for example, in UMAP, a popular way of initializing this Q of Y here is by computing the spectral embedding. Like that's a fine initial condition. It's like, it'll get you kind of close, and then we're gonna go from there, okay? So you're gonna guess what Y is. You could randomly initialize it. You could use the Laplacian eigenmap, do whatever you want. And then we're gonna optimize by computing the gradient of the loss function. Which way is downhill? How do I move all of these little points around so that it's going to optimize these things? And when it stops changing for long enough, that's when I stop. That's when my answer is going to be. Practically speaking, as you can see, these two algorithms are pretty closely related to each other, both in their formulation and their approach. The differences are mostly algorithmic, and it has some consequences because of this, the fact that in UMAP, the P's and the Q's are not normalized. One of the consequences is that because they're not normalized, it somehow makes it so that they're actually much easier to compute the loss function. It's faster. And it makes it so that the gradient is easier to compute as well. So the biggest difference between t-SNE and UMAP is not something grand or conceptual. It really is, it comes down to that UMAP is just faster. It is often like an order of magnitude or more than t-SNE, which means for the same data set, you can often compute and recompute the UMAP using slightly different parameters and explore your data more quickly than you would have been able to do with t-SNE. And in my opinion, I think other people might have a different opinion. In my opinion, that is the biggest reason to use UMAP versus t-SNE. You might hear other people say something about how UMAP is like more respectful of global distances and local distances relative to t-SNE. That is technically true. There's some theory around that. I think that is a true observation. But I think just like anytime you are squeezing a million dimensions into two, you're going to lose a lot of that global structure. The interpretation of close neighbors in t-SNE or UMAP space is pretty good. Like if you end up super duper close to each other, you're probably pretty similar. But the farther neighbors, exactly where they are, I mean, it's just a picture. We're just using it as a visualization tool. So the chief reason to use UMAP versus t-SNE is just, it's computational, it's very practical, it's just much faster. Okay, so that's at least a high-level explanation of t-SNE and UMAP and spectral embedding. We're going to have code examples coming up in a further lecture in a later video. And what we're going to do next is talk a little bit more about practical considerations and sum up this unit on nonlinear dimensionality reduction and what you actually do if you want to do manifold learning on your data set.